I was asked to kind of give a little bit of an overview of some of the new technologies, and some of not all of these will be new to you, but I wanted to kind of look at some technologies that really might change the way that we think about doing change detection from high resolution topography. So as Paula mentioned, I'm with the University of Houston and the National Center for Airborne Laser Mapping, which is a partnership between Houston and this cute little university on the West Coast, Berkeley. So when we talk about new technologies, one of the things that is continually evolving in the technology is the repetition rate of the laser scanners. So how many points per second they are recording. This is actually one of the slides that we use at NCOM. It shows from 1996 to 2014 the 6 different instruments that NCOM has actually used. You can see from the start here, we started with a 3 kilohertz system, 3,000 points a second, to now we're up at a laser system that is at 900 kilohertz. So a factor of 300 increase in the number of points per second that we can collect. When you talk about change detection, a lot of the legacy data sets that we're looking at doing change from recently are kind of in this 2001 to 2010 time period. And in that time period, we're still talking about a factor of 10 or 30 difference in the data rate. So we've gone from point densities of less than a point per square meter up to currently somewhere around 40 to 80 points per square meter. When we get to that kind of level of data, the resolution is actually approaching the accuracy limit of the instruments themselves. Although we've had a 300-fold increase in the repetition rates, the accuracy really hasn't improved significantly. I think we've gotten a little better with processing, but maybe a factor of 2, not a factor of 300. And this accuracy starts to become a little important when we start talking about really high data rates. So if we're talking about 40 to 80 points per square meter, when you talk about a laser system, it's not a finite point of energy. It's a beam that spreads out. And this beam has kind of a Gaussian distribution to it. So there's a probability attached with the laser being returned from a certain area. And when we look on the ground, we really have a circle or an ellipse of area that is illuminated by the laser beam. When we get a return, we don't know where within that beam it actually comes from. And so this gives rise to some uncertainty. If you want to reduce the uncertainty, you make the beam a little bit smaller. But unfortunately, for high resolution topography, that's not the best thing to do, because when you make the beam small, you decrease your chance of penetrating tree canopy and getting down to the ground. So you make the beam larger to try to get through it, but then you start oversampling the terrain. And so the important takeaway there is, even though you're getting 40 to 80 points per square meter, you're probably doing it oversampling, and you shouldn't expect to get, 10 centimeter resolution on the ground, because you're using a spot size in some cases that's maybe a meter diameter, and you're sampling at 40 points per square meter. So you're oversampling the terrain. This is important for the change detection because you might be looking at features that are below the resolution of the data and not understanding why you're not seeing them. In addition to the high rep rates, one of the other recent developments that have come out is multiple frequency lasers. So up until maybe mid-2013, most systems, with the exception of bathymetry, were one single laser wavelength. In the last 4 or 5 years, there's been several manufacturers that have come out with multiple frequency lasers. And why this is important is, typically for change, if you only have one wavelength, we're just using the 3D information from the data set. But when you have 3 active laser sources. This is the NCOM's laser. Here we have 3 wavelengths, 532, 1064, and 1550. You can actually do some active classification of the data. And when you can classify the data, you can actually do a better job of matching features between epochs. And so there's been a little bit of work here, but this is really an open question when it comes to change detection. Can we use that active spectral signature to enhance change detection beyond just using the 3D point cloud? Thursday and Friday, Chelsea and I are going to show you some techniques, but they only work on the point cloud. They don't consider any of this extra information. In addition to multiple frequencies, we're also seeing the prevalence of a lot of new platforms. There's really nothing structurally different from the airborne systems. It's just that we're starting to see a lot more Lidar systems mounted on UAVs, mounted on vehicles, and mounted on helicopters. And why this is important is because it changes the density of the data, but it also changes where you get occlusions in the data sets. If you want to try to match up something for change, you would like to have the same viewpoint every time, because it means that you're seeing the features the same way. If you're looking at them from different angles, it's very hard to actually match them up. And so it's an important consideration. You can't just say, well, I've got 2 point clouds, I should match these. You have to consider how the point clouds were collected to inform an accurate change detection. One of the other very significant advances in the commercial market is the single photon sensitive LiDAR, and I promised Jason I wouldn't steal all of his thunder on this, so I'll just briefly go over. All of the systems up until 2014 in the commercial sector were linear mode systems. We send out a really high energy laser pulse, and we have 1 pixel detector. That pixel detector measures a continuous profile of the return energy and picks out where the peaks are to give you some discrete return. So you get, if you digitize this waveform, you can get something, for example, like biomass, because it's giving you an idea of the amount of scattering in the wave. The military went a different way with their LiDAR sensors. They went with something that was sensitive down to the single photon. And the reason that they went this way is they wanted to fly at 30,000 feet above where the bad guys could shoot at them. And to do that, you had to be able to detect very weak signals. So they used something called Geiger mode LiDAR. Geiger mode actually uses the same detectors as the linear system. It just operates them in a way that they're a binary detector. They either have been hit by a photon or not. In their case, what they use is one very large pulse that flashes across the whole area, and then they measure the returns on an array of pixels. This is nothing but a digital camera, really. It's just instead of measuring passive light, they're actively flashing the scene and illuminating their own detector. Problem with this is because it's binary, you only get single returns. So it's either an on or an off. So if you're flying over the trees, you only get the top of the tree canopy, unless you play this statistical game, and this is what the military does. If you look at this digitized waveform, maybe 5% of the energy gets to the ground. Well, that means if I image the same area 100 times, I would expect 5 of those to come back from the ground. And so they use that statistical ability to stare at something multiple times and try to build up this profile to get to the ground. There's kind of a hybrid between the 2 of these, and this is called the single photon sensitive system. They use a low energy pulse like the Geiger mode, but they actually use very small beams of this, and they use a smaller detector array. I won't bore you with the electronics, but the way that they have this set up, they're actually able to do multiple returns, even at the single or few photon level. So this sounds all really good. Rather than having 1 pixel for every pulse, you can get 4,000 or 100 per pulse. And so right away you can see you can get a heck of a lot more data. Problem is, when you're at the single photon sensitivity, You're also sensitive to ambient light. You're also sensitive to any noise in the detector. And so when you look at what the data comes out from a single photon system, this is a sample from one of them. It's a jello mold. The Earth is actually right in here. But you can see there's significant noise all around this. This is what every single photon raw point cloud looks like. The raw data is contaminated by solar noise. You need to do some filtering to get rid of it. You rely on the fact that the noise is random while the signal is not. It's a fairly active area of research. The two commercial companies that offer this technology don't sell the software. They want to do all the processing themselves and give you the final product, and you trust that it's good. And I think Jason will have a few things to say about that. You can get from that unfiltered data to something that resembles a little bit more of a point cloud, but I think for the earth science community, there's a few things that you need to be aware of when looking at this data. So first, the good points. You can do a lot more data coverage. They talk about 1,000 square kilometers an hour collection versus ENCOM with our airplane, we can do maybe 50 to 100. Higher point density because their laser rates are a couple orders of magnitude higher, 200 megahertz for the one system. Problem is, because they're so noisy, you have to do some significant filtering, and they also, in a lot of cases, do some Gaussian smoothing to make the terrain look a little bit nicer. This also adds a little bit of noise to the data set. You don't get the same vertical accuracy that you would get from a linear mode system. And I think one of the really important things is in the critical zone where you have vegetation that from a laser looks random. You can't separate the vegetation from the noise in the single photon system. And so if you're studying the critical zone, this would be, pun intended, critical for your research. I think everybody's familiar with structure from motion as well. But this is another modality of collecting point cloud information. And people are going to start using this technology to difference against other structure from motion point clouds, maybe Lidar, DEM. It's pretty cheap to do. You can do with a couple $1,000s. Downside is there's no vegetation penetration, so you have to, this goes back to occlusions. If you're lining it up with a Lidar data set, Lidar will give you some returns from the ground underneath the tree canopy. The structure for motion just gives you the top. So if you're trying to do change, it becomes a little bit difficult. But in the end, it's still another way to get a 3D point cloud and a source of perhaps doing some change detection. So with that, those brief thoughts on the technology, I wanted to maybe warp that into why there's a need for tools. And obviously, if we look at historically, first airborne Lidar collects happened in 1994, 1995. From then until probably 2010, most collects were, what I would call virgin high-resolution topography collects. Never had been done before. Someone was going in there to get the first model so that they could do their geomorphology, update floodplain maps, etc. Starting probably about 2010, more widespread, we started seeing at ENCOM especially a lot more proposals where people were looking to do change detection from Lidar. And so the first one we did was the Elmar Kukapa earthquake in 2010. So that's the image on the right there. We have the vertical difference between the 2006 data set before the earthquake and a 2010 afterward. In the last 10 years, there's been a real explosion of these repeat surveys. We're working on a review article right now, and we're, I think, somewhere around 175 peer-reviewed papers that have done some sort of change detection using airborne Lidar. So fairly significant growth in that area. There's a lot of problems, and I think this is where the opportunity for a community response with tools is very important. Data density and accuracy is not uniform. A lot of the old collects were collected with old equipment at a lower accuracy. The Elmira-Kukupah earthquake, for example, the original data set was a point every 5 meters. The NCOM collect was 8 points per square meter. So you have a couple orders of magnitude difference in your resolution. It's really hard to determine change, but also figure out what is a significant change between those two DEMs. If you just want to do differencing of DEMs, you have to realize that horizontal motion corrupts it. If we look at this slide from Elmira-Kukupah, this is just a difference, but there was meters of slip along this fault, and so you can see it looks like the sides of the mountains moved. Well, no, that's not. That's because there was slip, and so when we do the difference, you see these kind of artifacts. The tools that are out there weren't necessarily designed or developed for earth science. One of the more popular ones is iterative closest point. It assumes rigid body motion. Earth doesn't really move rigidly in a lot of cases, and it's also kind of meant for hard targets in a lot of cases. The one I'll be talking about, particle imaging velocimetry, actually has nothing to do with change detection. It's a way to trace particles in turbulent flow, but we've kind of adapted it to also look at earth science. Some other problems is, and I'll talk a little bit more about this on Thursday, but the datum for some of these data sets are not the same. You get 2 point clouds from 2 different providers. They've processed it in completely different reference frames, and then you're trying to difference them. If you're not aware of those differences, you're going to come out with all sorts of exciting science discoveries. They're based on a small coordinate shift. The collection modalities, this is something I'm really concerned about with all of the new technology. I think one of the very large areas is that most of these changes, you create a change map, there's not really a rigorous quantification of what's the significance level. You know, what features should I be ignoring in this change? How accurate should I expect these volumetrics from this, this landslide motion to be, for example? The other thing is, in majority of cases, we're not incorporating any information about the underlying process to inform the model. When we do PIV on a landslide, we just difference point clouds. We don't put any information about how we would expect that landslide to move into determining the 3D motion. If we look in the literature, there's really not much done for evaluation of or comparison of developed methodologies. So if you have a certain science problem that you want to attack with this change, and you don't want to spend all of your time trying to figure out which is the best way to do it, you would like to have some sort of developed methodologies that you can go, this is probably the best technique for me to apply to my problem. Again, these tools weren't specifically designed for the science questions they're being applied to, and the error quantification is non-existent. There has been a little bit of motion in non-rigid 3D deformation, kind of ICP on steroids. This actually comes from the medical imaging community, where they're trying to match MRI scans across different time periods. We've been playing around with some of those methods, but to date, we've only kind of had minor success in the earth science with them. But I think a true non-rigid deformation in most cases is more applicable to a lot of earth science questions. Last thing, shameless plug for something NCOM. I apologize. No, I don't. This is the price of me coming, I guess. Every December, NCOM hosts a seed proposal competition. For any graduate student PI, they can propose up to a 40 square kilometer collect anywhere in the continental US. These are evaluated by our steering committee. It's a very small proposal. They only have to do 2 or 3 pages with a map. We're trying to push some specific areas, so proposals examining both shallow water bathymetry or change detection, kind of seems relevant, are encouraged. If you have any questions, you can email me here or our general email box at this one. This is kind of like your drug dealer giving you that first hit free, right? So we want to hook these PhD students on Lidar so that they'll come back and then the price goes up. So anyways, thank you for your time, and I'd be happy to answer any questions. Either really well done or really boring. I see. Okay. There's a couple in the middle. You can't answer this question. Yeah, you can. Go ahead.
This might be covered in today's talk, but you discussed the size of the cell that's being in the ground and how Geiger versus the other systems.
Yeah.
Can you overcome that though by just in more overlap? So if you sort of you kind of went by that fast. It sounded more worrisome than I thought. And for the linear case, if you increase your density and do a lot more overlap, wouldn't you be able to compensate to not being such a large market?
Yeah, I mean, when we talk about it, we talk about fill factor for the terrain, right? So if we use a smaller diameter, you're getting more points, but you're also having larger gaps. So to fill them, yes, you could cross-lap, overlap, but then it costs more money, for people outside of Berkeley. The Geiger mode is a completely different problem. They flash the whole scene, but their viewpoint is their detectors have a very narrow field of view, so they only look at a very small area of light coming back to them. It's the opposite problem. And our problem in the linear mode, it's focused or governed by the way the laser expands. In Geiger mode, it's governed by the lens on the receiver itself.
Bill, I have a couple of slides on that. Only 15-minute talk. I have a question, Craig. You had talked at a prior meeting on that about the kind of basically consumer LiDAR technology really improving, and we see it for on some vehicles. But you see, one way is sort of big technology sort of flying high, but what about lots of cheap LiDAR all over the place? What do you see as sort of the pros and cons of that?
There will definitely be lots of cheap LiDARs all over the place. The problem for this community is they're always going to be on roads. There does not seem to be much of a consumer push for drone-based LiDAR, and it's because no one is going out and buying a $100,000 model Tesla UAV. They're buying the $100,000 UAV car from Tesla. So yeah, there'll be a lot of data. They're not really worried about accuracy. Everything for them is relative to where the car is. They don't care if that point is in a real world coordinate system within a meter. They want to know how far that thing is away from the car, and that's it. So there'll be a lot of data there. I think we're a little bit further off from that being from an airborne platform where we can actually get a lot. The commercial market seems to have actually gone the other direction right now. They're trying to fly really high, really fast, and cover large areas because Google and Apple want big data sets. Apple wants the US flown once every 3 years, the entire US, from 30,000 feet at a point per square meter. It's really interesting. I don't know how much additional science will come out of that, though. Josh, your data set should have arrived today, right? Is that the question?
Well, no.
Okay.
Thank you. I saw that email.
Okay.
You said the density is going up.
Yeah.
Gangbusters. The accuracy is not changing all that much.
Mm-hmm.
What's the ultimate limiting factor on that? Is it the integration of GPS, the IMU, the laser, or is it one of those dominant?
It's all of them actually. The ranging accuracy of the lasers haven't gotten any better. They've been 1 to 3 centimeters for 15 years. IMU technology, they tend to, the highest level accuracy hasn't changed since the 90s in terms of pointing accuracy. When you start flying higher, it actually exacerbates the problem. The overall governing actually is the size of the spot on the ground. This causes significant error because you have this cone of uncertainty where the data comes from. It's not so bad for vertical, but it's really bad for horizontal. And so when you start talking about change detection, that's a significant issue with the horizontal. What needs to happen is, you know, if we could make the beam really small, have everyone not worry about eye safety, then we would be okay. But, you know, there's FDA gets involved and all of a sudden you're hurting people. And but it's really a combination. We've reached the limits of 3 or 4 pieces of technology. You know, fundamentally GPS accuracy is baby steps. You know, it's a percentage here or there. There's no big leaps anymore. So.
Craig, just to follow on to Josh's question, you said the vertical accuracy isn't that bad, but if you think, maybe you could speak a little bit about pulse length and how we might tighten that up to increase our vertical accuracy.
Yeah, so the pulse lengths are, 15 years ago they were 15 nanoseconds. The new lasers are 1 to 3. So we've already got an order of magnitude better there. The Geiger mode sensors use 200 to 400 picosecond pulses, so they're very short. What in terms of the ranging accuracy, though, it doesn't really improve anything a lot because we're still in the linear mode getting the full waveform, and it's still a matter of how well you can detect that peak. So even if it's a longer pulse, you still have just the one peak. The sharpness doesn't help too much. Unless where it really helps you is when you want to have multiple closely spaced returns, like in the vegetation. Okay. Thanks for your attention.